Today, we got an exciting talk today. Jimmy, just confirming you guys can see my screen correctly.
You see and hear loud and clear.
Perfect. Okay, let me just pull up that Q&A widget for myself to make sure I can catch any that might be coming in throughout the talk. Hey, everyone. I hope everyone's having a great Thursday. Uh, I'm here in New York City. It is a little gloomy outside today, but I'm excited to bring this talk. Hopefully, it will brighten the day a little bit. Today, we're going to be talking about what makes a good AV data set and the lessons I've learned from the front lines of sensor calibration and projection. A little bit niche, but really exciting area of AV dataset development and AV self-driving development as a whole. My name's Dan Garau, Machine Learning and Developer Relations at Voxel 51. And so even before we get started here, if you haven't known or this is your first time at a Voxel 51 meetup, and you don't know who Voxel 51 are, we're the lead maintainers of the open source tool 51. If you don't know what a voxel is to a video what a pixel is to an image. It's that volume element, such as the space-time volume of a video. If you don't know what the 51 is, well, it's always fun to have some guesses in the chat. So feel free to throw them out. I'll look and call it out to see if anyone has the right answer here. But be sure to just shout them out. I'm excited to bring this study. As mentioned, I've been working in AV datasets for about over a year now, working with multiple different customers, users, open source, as well as enterprise to help people build the best AV stack possible. Working with some awesome companies such as Porsche, Wave, Ford, GM, and more, all in the past, visiting them, talking with the researchers, meeting with them at conferences to understand what are the real pain points that are happening today. And I hope to kind of not only give you a quick synopsis on how the field is bringing up today, but also help kind of show you where the pain points today and how we're aiming to address them here at Voxel 51. So let's start with our race for autonomy. How does the field shape up today? What does this look like? And how are we kind of thinking about the problems? Well, I've been using this slide for about a year now. I don't think anything has changed. It's kind of always comes back to these three things. One, you needed a lot of GPUs, like a lot of GPUs, right? And it's no longer a question of, how often do I run the GPUs? What kind of tasks do I have the GPUs? Uh, Everyone is going to be running all the GPUs they have at all times at as much of a scale as possible with whatever tasks are available, right? This is going to be running all the time at these companies that are developing self-driving cars. And I guess that kind of helps. Let me set the stage a little bit too. That you kind of usually fall into one of two buckets here. You are either a classical OEM automaker. You think of all the cars you see driving on the road today, your Ford, GMs, Porsches, BMWs, Audis, Toyota, Hondas of the world are all investing in self-driving. You're also on another side, right? Maybe your non-traditional OEMs or your non-traditional self-driving shops, where things are like a Tesla, Waymo, Wave, and as well as some other ones that fall into this category, such as a Mobileye or other ones. But they all have a ton of GPUs, and they are trying to run these GPUs all the time. Uh, it's really easy to scale, as I mentioned. We can find tasks to run. We can find models to train in self-driving. And a lot of times, the car is not going to be driven by a single model, right? There's perception teams. There is teams to see, is this person going to cross into the street? There's teams to decide hierarchical of, do I decide to hit the squirrel or do I decide to swerve and things like that. There's so many different models at work in these kind of experiments in self-driving vehicles that there's always something to do and they're only going to get better. Next is the boundless amounts of data. Everyone in this space is already on the petabyte scale, right? They're working with petabytes of data. It's millions of hours. If you talk to the Waymos, the Teslas of the world, they have entire cities mapped, right, of just driving data. They know every corner store. They know every pothole. It's just hours and hours and hours and hours of drives that they're going to work with today. And then lastly, it's a very talented field. There's some incredibly talented engineers, and they are very tough to find. When you do have a very good AV engineer, they are very valuable within these kind of organizations, and they're easy to spot sometimes. But a lot of what is happening today is driven by the incredible talent and kind of ingenuity of the engineers working with it, which kind of makes it really exciting. This is a good segue of like, how does these fields kind of work up today? Well, right now, it seems to be that there are 3 teams really far ahead and everyone else that's kind of catching up. And I apologize for some of my bad AI bleed here in my image. But it's very clearly seems to be Tesla, Wave, and Waymo as the first 3. You might be able to bundle up some small niche cases that are also very ahead in the niche that they're trying to fulfill. Mobileye is kind of similar in this case. But when it comes to overall OEMs who are trying to build self-driving and either put them into their own vehicles or sell them to other providers, these 3 are right ahead. What's really, really, really exciting about this is that they all have very different approaches to solving the problem, and we don't know who's right. Tesla, if you're not familiar, is no LIDARs, right? It's very camera-based. They are trying to do everything with only perception off of images and video feeds, no LIDAR. Is it a great approach? I don't know. I mean, they have great results. Will it pan out in the long run? We don't know. But I can say that they are the only one that are doing this. Wave is also right up there. And Wave's unique approach is simulation. They are experts when it comes to the simulation field. They are simulating so many different scenarios. They have really great simulation models to generate new simulation environments. They're driving something like I've once talked to a researcher 20 times in the sim for every single time that they're actually driving on the road. So while you might not see as many Wave vehicles, especially in the US, as you would a Tesla or a Waymo car kind of driving around a Phoenix or something like that, gathering data, Wave is doing all of these kind of in simulation as one of their main strategies. And then lastly, Waymo. I think everyone probably should be familiar with Waymo here. They have insane sensors, calibrations, LiDAR scanners, all on their car, which give it a very unique look. And I mean, they just have really good talent, really good models, really good approaches to doing everything. Their kind of methodology is build the best model, build the best sensors, and kind of have the best company. There's not going to be a easy solution to the problem, but if we keep on cracking on, trying to solve difficult problems one by one with our car, then we will be able to do it. And it's been very successful so far. And then lastly, I just want to touch on everyone else. It's not that everyone else doesn't know what they're doing, right? It's just that self-driving is a field that's almost more comparable to a traditional manufacturing or electrical engineering field than it would be to maybe some other model development fields where you have to make the mistakes along the way. And the people in the front, especially the Tesla and the Waymos of the world, are not going to be telling you all the answers to all the problems you're going to encounter, right? And we don't have these situations where like a new model architecture changes everything, or we found a new method that's going to solve the problem, make it 50% better, or anything along those lines, right? You have to start. You got to invest in your team. You got to invest in that talent that I've mentioned. You have to make mistakes. You got to drive the car. You got to let the car make mistakes, both in sim in the real world, and you got to fix them and iterate, right? It's a timely process. And time is one of the most crucial elements to having a well-working self-driving car, right? It's how you can maximize the time that you do have to get it there. I'm going to answer a quick question. What does top-tier talent make the difference? If everyone's using the same data algorithms and architectures? Great question. 2 answers here. One, they're not using the same data algorithms and architectures. They're using very different ones, right? People have different ways of data sources, different ways of ingesting the data sources, different architectures are going to do different methods. And that's kind of where the talent comes in head, right? Is what pipeline from end to end, and we're going to talk about this, is best for your way that you're building your self-driving car, right? Tesla, for instance, there's no LiDAR, right? So you can't say they're using the same data. They're using completely different data than a Wave or a Waymo, right? Wave is choosing to do this all in simulations, right? So you need to have really talented, like true engineers that can envision the whole stack, invest in the correct places. It's not that every decision is a wrong one or a right one. It's what are the most efficient and valuable decisions that are going to get you to stay on pace or ahead of the rest of the competition, right? And that's only a talent-based. You need to have good engineers to be able to do that. So let's focus on data sets. What actually makes a good data set in this case? I have this line on the top here. I want people to kind of keep it in their mind as we move through. Progress is verification. Verification is progress. Everything with a self-driving car, right, today in 2025 is proving that the car is safe to drive on the road, right? Safe enough that someone will take a taxi ride, safe enough that someone could fall asleep at the wheel and they'll be okay, safe enough that you would put your kids in the back seat and you'd feel comfortable with it, right? That is the goal here, right? It's not to make it fast, it's not to make it fun or any of these kind of things. We want to verify that we will be safe in the car and it won't make danger to other people. So when we say progress is verification and verification is progress, we always are working towards that end goal, right? How can we prove and justify and make sure that even in the cases that we've seen before and the cases we haven't seen before, that the car will make the right decision? So let's clear up some misconceptions about the field. And some of these used to be true, some of them are not true anymore. The first one is kind of just like ChatGPT, right? More data is not better data anymore, right? So similarly to how ChatGPT or similar models of that, Gemini, Claude, they've already trained on the whole internet. You're not going to give it any more information that is going to robustly improve the model performance, right? It's not a throw 10 million more hours at the problem and the model's going to learn how to drive all of a sudden. It makes perfect K-turns or something like that. We need to be very selective with the data that we choose to add on to our self-driving cars at this point, because we know that if it was just more data, it would be a solved problem now, right? But we have edge cases. We have rainy days at night. We have snowy crosswalks with the lines covered, right? Like these very weird, interesting edge cases where it's not a matter of just driving the car every day for 2 more years and we'll have self-driving cars. You have to find the edge cases, identify the edge cases, and make sure you're training on kind of the most difficult problems today in self-driving. The cars are good enough to kind of do the practice law drive through. Next, all the data we need does not exist today, right? So an easy way to do this is kind of humans will understand obvious things, right? So it seems obvious to us, but if someone is running across the highway on the other side of the highway and they're about to jump the median and then run into my highway, I will be hitting my brakes the moment I see the guy running on the other side of the highway, right? But for a lot of self-driving systems today, unless you're predicting, hey, I think this lunatic is going to run in front of my car in about a minute or 30 seconds or 15 seconds or whatever the amount of time is, right? Humans will understand, and we have the perception to understand that is a problem I need to address, even though it's not in the rule books of driving, right? It's not the cars right in front of me. It's not on my side of the street. That is an off-plane thing. This is a crazy edge case that we need to consider for cars, right? And we might not be able to find. There might not be video evidence of my self-driving car in the field with a lunatic running in front of it. We need to make sure that we are building these edge cases, both in simulation or in real life, to make sure that we cover all the cases that even might not ever come up, right? And make sure that the model can make the perception jump to adapt correctly to events it's never seen before. Lastly, sensor placement is not a solved problem. This is a quick one, but just things like Tesla doesn't have LIDAR, right? I keep saying it. This is really weird because everyone else uses LIDAR. Even when you talk to people like Wave and Waymo, the LiDARs are in different places, the cameras are in different places. Some people think too many cameras are a problem. Some people want multiple LiDArs. There's we're not sure how we feel about radars and open question, things like that. So sensor placement is not a solved problem. These data sets come in many different formats, and I would fully expect every automaker and AV developer to move and adjust their sensors in the future, right? It's not for sure it's going to be in these locations on the car or anything like that. There are some things that we are very confident in, though, right now, in that usability starts with calibration, right? Quick question. Why does Waymo have a sensor on the top and Tesla does not have one? Ask Elon Musk. He doesn't tell anyone why, right? This is just their way of doing it. It's a cost efficiency way. They think they have enough information. That's all you can really say, right? There's no right answers, right? So why? Why? Because they chose to, right? It's we can't have a positive way. They'll have their arguments. Waymo will have their arguments. We can't prove anyone's right today. Usability starts with calibration. You can imagine, I don't want to overboard this, right? Because it's very simple if we think about just it from kind of, don't make it too complicated of a problem is what I'm trying to say. If your data sets won't work properly in model training because you haven't calibrated correctly, because the data was loaded off the car correctly, because your images are corrupted, well, then you're just going to waste all this money, right? Remember, we said that time is the most valuable thing. We need to be efficient with how we spend our time. If you're using incorrectly calibrated data sets, well, you're just wasting time because the model's not going to train as well, and you're not going to be able to do all this stuff. You have to do this before anything else. Second, synthetic data is not a maybe, but a must. We just talked about the lunatic running across the street. Let's think of a really bad case scenario. Let's say my car hit grandma, right? My car hit grandma. I'm sorry, grandma. I am not going to be able to tell grandma to go back in front of the car the next time it's trained and say, like, grandma, there's no chance it's going to hit you this time, right? I can't do that, right? I have to synthetically do this. And NeRFs, Gaussian splats, simulations are dominating the space more and more every day. We did say that more data is not better data. More metadata is almost always better data, right? And so we're kind of learning this on the fly too. I'm sure other people like Tesla's, the Waymos, and the Waves have already thought about this in some ways, and they're solving it. But when we think about metadata, and we're going to get into this later, is there's so much going. Like there's so much you can think of where it's like, what is metadata, right? Is metadata saying like, hey, is there a traffic light nearby? Are you on a bus route? Is it the school year? Is there any specific traffic laws I need to know of? No right turns on red between 9 and 5, right? All these different things. The more information you can provide and keep at the scene, frame, sample level, the better overall data set you're going to have for search reasons, as well as for model evaluation reasons, as well as model inferencing reasons. Basically, the more we can contextually understand each sample past just an image with no timestamp, with very minimal data around it, that is not very valuable to me compared to this really rich and robust sensor and metadata suite that's filling up my data set. That's what we really want. So quick comparison about what bad data and good data can look like here. Here we have a sensor miscalibration, where even though that these came from the same frame, the LIDAR sensors, everything from initial evaluation would tell you that this was a correct scan. There's no miscalibrations. This is coming from the Waymo data set in this data set. I shouldn't say miscalibrations. There is a miscalibration, but you got it all from the same frame. We can clearly see that the LIDAR shadow is kind of lagging behind the actual woman here, right? We want to make sure that these are aligned, similar to how we see nice pillars on the right. We don't see that here on the left. So this would be a case of poor alignment. And on the right, we have a case of good alignment inside of 51. So how do we actually go from raw logs to usable data sets, right? This is kind of our big slide. We're going to keep on coming back to it. We're going to talk about this, but I'm going to walk through the journey here from logs to data set. First, this is a little opinionated. Collect all the raw sensor logs and know where they're located, right? So when I say raw sensor logs, I really mean like the PCD, JPEG, MP4 level, right? Some of us here might be familiar with like ROS bags and TF records and things like that. I would make it more atomic, right? If you can have the PCD and you can afford to have the PCD and the JPEG and the metadata and the sensors and JSONs and all this stuff, whatever is the most raw form of that, start there, right? This makes it so much easier to kind of keep track and make everything logical. It makes the search process a lot easier down the line. If you have like a compressed TF record, it's kind of hard for me to find individual frames across a petabyte of data, right? If I have an S3 bucket with just PCDs and JPEGs in it, well, now it is a lot easier for me to attach a database to that and vector search it and RAG or what all these downstream use cases. So I highly suggest you unpack and decode if needed. Next, step 2, we want to add all the metadata in a dataset scene frame sample hierarchy. What does this mean? Well, for dataset scene frame sample hierarchy, the data set is whatever data set context you're working in today. It can be something as all my data, a petabyte. It can be something just as rainy days, whatever you're working with this, but whatever, start the problem, define what the problem you're working with is today. Scene is basically a drive, and this cannot even be one continuous drive. It's basically like a 40-second or a minute-long drive of like, hey, this scene is important, or I've identified this as important, or maybe it's not important and we're going to throw it out. But segment it into scenes. Then frames, there's the individual frames every time, every sensor's fire. And then the samples are the individual samples, right? That's the left camera, it's the top LIDAR, it's the right camera, right? Split it into this type of hierarchy, and then add all the metadata. What is metadata? We'll talk about that next slide. Calibrate and validate all the intrinsics and extrinsics for each sample. You're right. We don't want to waste money. We don't want to waste time. If this data was corrupted coming off the car, if it's not lined up correctly, if something happened incorrectly in this pipeline, we need to validate before we do anything really expensive, right? So do that step 3. Step 4, add your annotations. Now that we have the intrinsics and the extrinsics, we can add our annotations and kind of do this both in the 2D and the 3D space. If you're not familiar with self-driving annotation, it is insane when it comes to the level of detail. So we're talking 2D detections, 3D detections, semantic and instance segmentation, both in 2D and in the point cloud, depth maps, normals, HD maps, key points for things like drivable areas, the limbs on a person walking into the street, maybe points of interest in the environment, drivable areas I mentioned. How many lanes are in the field? Can I switch lanes right now? Can I not switch lanes? Where can I park? Where can I not park? Ego mask is really important. That's the mask of the car you're driving. We don't want our car to detect a car as our car, right? You can see why that would be a problem. Dynamic actors, what's moving in the scene versus not moving in the scene. So I know that I have to predict its motion down the line and more. There's much, much more we could dive into here. But it is very, very robust and it's very, very expensive, right? We do not want to have all of this on every single one of our samples. You would be out of money in the first month, right? We want to make sure that we're only doing this super robust annotation on the important driving scenes. And then lastly, project the points and verify, right? We're going to wrap all this stuff together. We go back into the last slide here where we want to verify, right? Our bounding boxes are aligned. We don't have any shadows like this. It's just basically the last visual check that everything is correct, and then we can move on to training. So what is metadata? Well, here is the metadata that I've identified for being important from a Waymo driving data set, for instance, right? And Waymo tends to be one of the best ones. And I'm just going to call out some of these. I'm not going to go through everything here. But the idea I want you to take away is that there's a lot of metadata that you should have on every single sample, right? Especially at the frame level. So we need to know the timestamps. We need to know the intrinsics of the camera. We need to know where the car is in respect to its motion from the previous scene, for example, in the next sample or the next frame. So that we usually call that T-rig worlds and T-sensor rig. These are our poses. So this is from the sensor to the rig transform. This is from the rig to the world transform. There's a couple other ways to express this, but this is the way I've been using it. We need to know what clip ID we're in. We need to know the velocity of the car, direction of the car, the start and end timestamp of the frame, the rig timestamp, where that pose comes from. We need to know the ego mass, the camera, what was the shutter time, shutter direction, camera trigger time, camera done time, the distortion coefficients, any type of annotations, and even more, right? The LIDAR, intensity, elongation, 3D bounding boxes, semantic segmentation, instance segmentation, range images, spin directions, point timestamps, inclinations, azimuths, range image indices, where were the second beam reflectors, right? So we shoot those LIDARs. If it reflects again and comes back to our LIDAR sensor again, we call that a second beam reflection. Can we identify which points are a primary and a second? It's very intense, right? You can see why it just gets really messy really quick. And so let's go through some common failure points here. First off, where do I see, right? So I'm just not going to say that everyone has these problems. I've talked to people in open source. I've talked to people in enterprise, billion-dollar companies, some guy that's really just interested in AV in college. They almost all trip up over the same problems. One, they all trip up on this step. Everyone kind of knows where their LiDARs and JPEGs are. That's kind of an easy problem. You should know where they are, whether they're in the right order and everything like that. That's a step 2 problem, right? You're struggling to have the metadata. You can't find the metadata. You never heard of an azimuth before yesterday. You didn't know that your LiDAR even recorded secondary ray bounces, right? There's a lot of learning curve to kind of what everything these sensors are possible to do. And if you're an AI engineer that's not really like familiar with hardware and things like that, then that's going to be an issue. And a lot of people trip up on this. The second one Skip the calibrating. This is another one where like assuming your sensor is not broken, right? You're gonna have like good intrinsics and intrinsics, right? Assuming that like you already passed step 2. So you're not gonna like have these situations usually, unless you're in a simulation where this step actually is a problem. Like your camera's not gonna lie to you. The shutter speed hasn't changed drastically, things like that. We just need to verify that they actually do work for the data set we're on. The next one you'll trip up on is this annotations, right? Why? Because you don't have them, right? Like the car doesn't have all of this stuff coming off the sensor. You have to add this later. And a lot of the times today, it's human annotated, right? We're moving towards automatic annotation, but we still have to keep that human in the loop because it's still self-driving cars and there's lives at risk. So how do we actually find and add all these different things? It's really expensive, really, really, really expensive. And we can't afford to do it on our entire petabytes long data set. And then lastly, projecting and verifying the points. People skip this. People skip it. They don't think it's fine. You'll have entire workflows where you're doing reconstruction, that you're training models, you're doing all these things, and you actually haven't checked to see if it's actually calibrated as best as possible can be. Even alignment can be things like alignment's a big deal when you're driving 80 miles per hour or something like that, right? If you're only taking a pose every half a second, quarter of a second, well, my car, how far has my car driven in between seconds? And the cameras need to be making sure that when they fire in between the rig, that they're aligning correctly. We need to help kind of interpolate with velocity in mind and all those kind of things. So we want to make sure that we're always projecting and verifying the alignment. Basically, it's a last check for everything above. However, if you do all those things, you're going to end up being like this guy. And I know this is like a quick turn on here, right? But this isn't actually the real problem. This stuff's very important. And if you want to have a well-trained data set, you're going to have to need to do all this stuff.
Hey,
But
Dan, quick time check, 5 minutes.
5 minutes is perfect. No worries. The real problem here is before and after all of this. Why? Because we need to close the loop. Data's going to come off the car, and that step that we just saw of those 5, 6 steps, everyone is going to do individually. They're going to do it their own way. And this leads so that your team, users, people in the open source community can't actually share any of the findings that they've had. Even once it's in the system, if you can't find what you need, it's all ROS bags and TF records compressed on some server somewhere. If you can't say find all rainy crosswalks, then it's useless. Then you're not going to be able to find those edge cases we talked about. Post pipeline, what's the point if it's all custom? If everything is custom, everything is completely made by this one team that has written all their own Python scripts and all this kind of stuff, you'll never be able to adopt new techniques, right? A new model will come out the same way we see with ultralytics. We were talking about this in the last talk. New ultralytics, YOLO V95 comes out. Everyone can use it right away because they've already been using ultralytics. If you're all custom, you're going to have to remake the entire pipeline just to get to that model. This goes for sims, synthetic data, diffusion models, and more. However, Voxel 51 is coming to the rescue here, where we are building this physical AI workbench, which will allow you to all stick to one standard here. So once you ingest that data in, you follow the steps that we've mentioned, we can actually then automatically measure the dataset quality of your dataset, do all that metadata, sensor completeness, alignment checks for you automatically. And that way you get this high quality data set where then you can then go to all these third-party tools, and we're actually teaming up with NVIDIA to do this. So assuming you pass your data set audit from your AB data set, you'll be able to do things like search with Cosmos video search, reconstruct with NVIDIA neural reconstructions, and augment with Cosmos transfer. This allows you to do really exciting things downstream. So how do we envision this? And there's docs here. I have QR codes. Jimmy will send these out. Always feel free to scan the link, and I'll leave this up later. But we have docs on how to get started with self-driving today. Ingest, you'll see our images and our cameras and point clouds loaded incorrectly. Then we're going to calibrate and validate. This is coming soon. It should be out in the next 2 weeks to be automatically doing this. Next, we're going to annotate. We have another thing here for us to scan from the docs. How to add annotations, leveraging embeddings, use the model Zoom in 51 to add auto annotations. It will look like this after your annotations are loaded in correctly. We even have a new thing that we're bringing out soon called verified auto labeling in our 51 enterprise version, which will allow you to automatically add labels and annotations in and help you find those best and worst case ones and keep the human loop and in the most performant way. Lastly, You want to do that project and check alignment. Make sure that everything is correct, project everything. That's going to be part of that audit open source code that we're going to be releasing soon too. And then lastly, once everything is checked off, you can export and go, right? This is when you can start using things like NVIDIA Cosmos Transfer, where you can change sunny scenes to autumn days, to winter days, snowy days, rain, nighttime, whatever you need to change about the scene, you can automatically do to have more coverage. We can even do things like NVIDIA neural reconstruction, where you can build a neural reconstruction of the scene, where the top one here is completely real, the bottom one is fake, it's a reconstruction. You can then add new actors into the reconstruction to make whole new environments, scenes, and frames to help work with. And this is really where I see the future of AV going, right? We need to standardize this. 51 is open source. We're happy to be the single source of truth here, where if you can automatically know all that metadata that we saw before, if we know where all the camera shutter times is, where the point clouds, the annotations are, well, we can basically build together an ecosystem where we can go to all the different models downstream. We can go before and ingest new data. All of this happening automatically while taking advantage of enterprise tools such as that verified auto labeling, visual question answering, APIs, map and traffic data, and more, all of it. So the users will be able to perform AV workflows with confidence. You're not wasting that time. You're saving and efficiently using your time because you know your data sets are robust and high quality. Because it's all in a single source, we can share algorithms and advancements and make it easy to import from new data sources if you change those sensor calibrations. And then lastly, you're going to get access to all these vendors, such as NVIDIA and all their AV tools that they're building, all accessible within a few clicks, where you can understand your issues and what tools will help fix them, and leverage both external and internal tools to build your perfect pipeline. So I'm going to pause here. I know it's end. We're getting close to time. I'll leave a link to code to a whole workshop I built on self-driving data sets. I have a LinkedIn QR code to connect with me if anyone has any follow-up questions. We do have some questions in the Q&A. Drop them if you have any more. I'll text them if we have not enough time. But Jimmy, do I have enough time to take these two questions here?
Why don't you take one?
All right. I'm going to read the second one. Interesting insights. Can you shed some light on how the outlier detection is performed to determine information-rich samples that are subjected to further annotation, apart from clustering the embeddings of some sort? Is there some unique in the domain of autonomous driving? Yes, Lucas. We see a lot more investment into specific models for outlier detection in autonomous driving. Once again, there's no concrete answers in self-driving. Microsoft is building really great SLMs, small language models, to help do VQA on AV datasets to help you find things like dangerous driving, or things like that, or dangerous scenes, objects in the road, as well as Cosmos. NVIDIA is building embedding models specifically for the AV space that are vision and language. So I can say things like find every cut in, find in every dangerous sign, find in stomping on the brakes, whatever it might be. To help find these outliers across petabytes of data, and then we can choose to do the annotations on top of them. I'll answer the other questions, but thank you for your time. This is something that we're really excited to bring to everyone soon in 51, and I'm always available online on LinkedIn or in our Discord community to answer more questions.